Hi everyone, I'm Chen Hao from Osaka University. I'm happy to present our ECCV 2024 work, Deep Polarization Cues for Single-Shot Shape and Subsurface Scattering Estimation. Given four linearly polarized images of a translucent object along with an object mask, we jointly estimate the homogeneous subsurface scattering parameters, surface normal, and depth. There are various types of objects in our daily lives. Some can be represented using an opaque surface, while others can be modeled as volumes. However, translucent objects like wax, marble, skin, or glass of milk cannot be accurately represented just an opaque surface or a volume. In fact, these objects exhibit both surface and subsurface scattering. Correctly modeling and estimating both types of scattering is important for downstream tasks like relighting and material editing. Light is an electromagnetic wave. Its amplitude determines brightness, its wavelength corresponds to color, and its vibration direction causes polarization. With standard RGB cameras, we can only capture brightness and color. However, with the latest polarization sensors, we can also capture the direction of light vibrations. Polarization is also a valuable cue for recovering translucent objects. The captured polarization signal contains both diffuse and specular polarization. Specular polarization results from single-band surface scattering, while diffuse polarization arises from light undergoing multiple subsurface scattering events. The subsurface scattering parameters control the ratio between diffuse and specular polarization, which in turn affects the final polarization signal. As shown in the example on the right, when the liquid changes, the subsurface scattering parameter also changes, leading to significant shifts in the polarization cues. In this slide, we present an overview of the proposed model. We train a cascaded network to estimate all the necessary parameters. The geometry is represented by surface normals and depths, while the illumination is modeled using spherical harmonics and flashlight intensity. The subsurface scattering parameters are described by volumetric albedo, the extinction coefficient, and the Henry-Gristin phase function parameter G. Our input consists of four polarized images with different polarization angles, an object mask, and a computed min-max images. We first estimate the shape and illumination, then we use the estimated geometry and illumination to guide the subsurface scattering estimation. Additionally, we propose a novel reconstruction network that takes four pure BSDF images and the estimated subsurface scattering parameters as input to further reduce the ambiguity in subsurface scattering estimation. In this slide, we introduce the min-max images. These are the minimum and maximum intensities observed when rotating the polarization filter, and they can be computed analytically using the four captured polarization images. The main image can be interpreted as the image with reflections removed, providing a useful cue for the model to help separate surface scattering from subsurface scattering. Measuring the scattering parameters of a large number of real-world objects is time-consuming, especially for translucent materials. To address this problem, we use synthetic objects to train our model. We render our synthetic data using MISPA 2, which provides ground truth parameters for illumination, geometry, and subsurface scattering. Here we show the shape estimation results compared to the existing shape from polarization model. Our model demonstrates the ability to accurately estimate surface normal for both synthetic and real-world translucent objects. For the subsurface scattering parameter estimation, we also compared our results with an existing model that uses only intensity images as inputs. Our estimated subsurface scattering parameters are found to be much closer to the ground truth. Here we present an interesting application of our method, material transfer, which is important for augmented reality and virtual reality. We also present the quantitative results. Please refer to our paper for detailed explanations. Thank you for your listening.